Now we're looking at what it means for a function to be continuous at some value x equals a. And so kind of just an intuitively what's happening, not mathematically written out, but basically it's a continuous at some value x equals a. If you can draw that graph without picking up your pen or pencil at that value x equals a, if you have to jump and pick up the pencil to move it, then it's not continuous at that value. But that's not mathematically correct in the sense that it's not defined explicitly. So we are going to do this. And now, because we have the tools, we can show that a function is continuous at some value x equals a or not continuous there. If it's not continuous there, then it is said to be discontinuous. Okay, so continuity at, actually in their book say x equals c, but it doesn't matter, x equals c, x equals a. So we say a function is continuous at x equals c if the following hold. Okay, so three things has to hold in order for it to be continuous. If one of these things doesn't hold true, then we can stop and say it's discontinuous there. So first thing that has to hold, and it doesn't matter actually the order, but f of c. So if we plug in c, wherever we see an x in our function, that this is defined. So this is f of c is defined. So c has to be in our domain, but if it's not, then it won't be defined and we could stop. The limit as x approaches c of your function f of x, this has to exist. So, and remember, in order to show that a limit exists, so we need to show that the left and the right, we might have to show that the left and the right, so the limit as x approaches c of f of x on the left is the same as the limit as x approaches c on the right. And then 3. The last thing that has to hold is that limit that exists as x approaches c of f of x. It has to be the same as if we went in and plugged in c wherever we saw an x in f of x. So our answer for 1, it was defined, what is that y value when we plug in x equals c? That has to be the same thing as our limit. So if that's the same, then we can say that it's continuous. The function's continuous at x equals c. Okay, so if any of these don't hold true, then f of x is discontinuous. At x equals c. So if you were looking at a graph, you didn't have the function, it's going to be, there's 3 types where you could have discontinuity. So there's 3 types of discontinuity. kind of similar to where the limits might not exist. Okay, so 1, you might have a jump in the graph at x equals c. So here's a case that could happen. You might have an asymptote, vertical asymptote.
Professor,
Yeah.
after you're done with this, can you scroll back up a little bit?
Yes. Yes.
Okay, thank you.
Yeah. So vertical asymptote at x equals c. So that is, okay, if we have c here, we have a vertical asymptote. So if this is maybe coming up like this, it's going down like this, it doesn't matter. Could be going in the same direction, but remember it's never crossing. We talked about graph never crosses a vertical asymptote. And then the last case, you might just have it where you have the limit actually exist, but we have an open hole there. It's not defined there. This right here, this last case scenario, we can actually make this continuous. So this last case is called a removable discontinuity. Because if we say, okay, this is our function, maybe give it a piecewise function. So this is f of x for all values except for x equals c. And then when x is equal to c, we could say it's this point. And then if that's the case and we fill in this point, we've now just made it continuous there. So those are the 3 different cases that could happen while we're looking to see if a graph is continuous or discontinuous at x equals c. So we're looking at a graph and determining where this is discontinuous. All the values of x where it's discontinuous. So just what we were talking about, looking at this, I can see I have a vertical asymptote at x equals -5. And so, and if I had to draw this, right, I have to pick up my pencil to get this piece. So 1, it's discontinuous at x equals -5. So for that let's say was A. For B, if we look at the limit as x is approaching -5 on the left-hand side of this function f of x. So coming in on the left, right, and following the graph, it's never going to any one particular y value. This is going to positive infinity. So limit doesn't exist, but when it's going to infinity or negative infinity, a lot of times we'll say what direction. If part C said, look at the limit as x is approaching -5 now on the right. So again, as we're coming into -5 on the right-hand side, following the graph, as you're getting closer and closer to -5, notice this is shooting downwards. This is equal to negative infinity. D wanted us to find the limit. Well, as we're approaching -5 of f of x, this is where I can say it doesn't exist. And identify which condition isn't being met. There's actually there's two conditions that aren't being met. The limit does not exist. That was one of them that is not being met. But the other one that's not being met is x equals -5 is not defined on that graph. And so f of -5, if I plugged in -5 wherever I saw an x here, there's no point. And this is also does not exist. So because of these two conditions, makes it so it's discontinuous there. Show discontinuity. Okay, so that was one value where it didn't exist. If you look at it and you follow the graph, notice there's this open circle when x equals 0. And so it's also discontinuous. Put it up here. At x equals 0. It wanted us to look at the limit as we're approaching on the left. So limit x approaches 0 on the left of this function. So the y value, are we hitting any y value? Are we getting closer and closer to any y value on the left? Well, we are, even though it's not defined right there. Notice we're getting the y value of 0. And if we look at the limit as x is approaching 0 on the right, so coming in on the right, following the graph, notice that that y value we're getting closer and closer to is also 0. Well, left and right hand limit are giving me the same value, and so the limit does exist and it's 0. But the condition that doesn't hold here is that it's not defined there. So it is discontinuous because f of 0 does not exist. Okay, so those are the two places in this that it is discontinuous. So notice this one's a little weird at x equals 4, and we'll talk a little bit more about this when we get into derivatives. But notice it's smooth and continuous. If I'm looking at the limit as it's approaching, I would say maybe 0 in each cases. Okay.